use Rolle's theorem to show that the function x squared minus the square root of x has a critical number in the interval 0 to 1. Then find the value of this critical number, or critical numbers. There might be more than one. Okay, Rolle's theorem. In order to use that theorem, the function f of x must be continuous on the closed interval from 0 to 1. X squared is continuous for all x, and the square root of x is continuous on the closed interval 0 to infinity, closed at 0, so including 0. And the difference of continuous functions is continuous, so this function f of x is continuous on the closed interval from 0 to 1. Then we also need f of x to be differentiable on the open interval to 0 to 1. And the derivative of our function is 2x minus the derivative of the square root of x is 1 over 2 times the square root of x. And so f prime is not defined if x is 0, but if x is bigger than 0, then 1 over 2 times the square root of x is defined. So this function is defined for all positive x. So it's defined on 0 to infinity, meaning that f is differentiable on the interval 0 to infinity, and therefore it is differentiable on the subinterval from 0 to 1. The next thing we need to use Rolle's theorem is that the function must have the same output at both endpoints. So if we calculate f of 0 and f of 1, in order to use Rolle's theorem, these two values must be equal. So f of 0 is 0 squared minus the square root of 0, which is 0 minus 0, and that's 0. And f of 1 is 1 squared minus the square root of 1, and that's 1 minus 1, so that's 0. So they are equal, and so we can use Rolle's theorem. All of the conditions of the theorem have been satisfied. All of the hypotheses have been satisfied, and so we can use the conclusion. And the conclusion says that there exists at least one number usually referred to as C in the given interval, the open interval 0 to 1, such that f prime of C is equal to 0. So in our problem, we want to show that the function has a critical number, and when the derivative is 0, we have a critical number. So in other words, the theorem guarantees the existence of a critical number in the interval. So C is a critical number for f in the interval 0 to 1. So the first part of the problem has been demonstrated. We have shown that the function has a critical number in the open interval. Okay, now we have to find the value of that critical number. So we will calculate the derivative of our function and set it equal to 0 and solve for x. So we will take this equation here and we will solve it for x. Our derivative is there. 2x minus 1 over 2 times the square root of x is equal to 0. So 2x is equal to 1 over 2 times the square root of x. And if we move the x's over to the left and the numbers to the right, we get x times the square root of x is equal to 1 over 4. And x is the same as x to the first, and the square root of x is the same as x to the 1/2. And when you multiply these, you add the exponents. So in other words, x times the square root of x is the same as x to the 3/2 power. And when you have x to a power is equal to a number, then you raise both sides to the power, in this case, 2/3. Take the reciprocal of the power. And so that's equal to 1/4 to the 2/3. So multiply these to get 1, which is why we did that. And then we get 1/4 to the 2/3. There's an answer. That's a number between 0 and 1. It's positive, and 4 to the 2/3 is bigger than 1. 4 to the 2/3 is the cube root of 4 squared. That's the cube root of 16, which is somewhere between 2 and 3. So this fraction is bigger than 1/3, but less than 1/2. So our solution here, which is the number C that we were looking for, is in the interval 0 to 1. So there is our critical number, 1 over the cube root of 16. And if we really want to get fancy with it, 16 has a cube root in it, namely 8. And so this 8 can come out. The cube root of 8 is 2. So 2 times the cube root of 2, we could plug that in for our 16. So the C value is 1 over 2 times the cube root of 2.